There is a rule in astrophysics. It has been tested, verified, and agreed upon by every major observatory on Earth. It has been refined over a century of observation. It sits at the foundation of everything we teach about how stars form, how they live, and how they die. The rule says that a star cannot exist above a certain mass. The physics will not allow it. Above roughly 150 times the mass of our Sun, a star becomes so luminous, so blisteringly hot, that the radiation it produces tears itself apart faster than gravity can hold it together. The outward pressure of light exceeds the inward pull of gravity, and the star destroys itself before it can grow any larger. Stars don't get bigger than that. That is the rule. And it held for decades. Telescope after telescope, galaxy after galaxy, the upper end of the mass scale stayed right where the physics said it should be. Around 150 solar masses, give or take. The numbers were consistent. The models were confirmed. Then someone pointed a telescope at a small patch of sky 165,000 light-years away. And the rule broke. The object has a name, R136a1. It sits inside the Tarantula Nebula, a vast star-forming region in the Large Magellanic Cloud, a small satellite galaxy orbiting our own Milky Way. For most of human history, that patch of sky was just a faint smear of light visible from the southern hemisphere. Sailors used it for navigation. Ancient peoples wove it into their mythology. Nobody suspected what was burning at its heart. Then in 2010, a team at the University of Sheffield pointed the Very Large Telescope at its center and measured what was there. What they found stopped the room. R136a1 has a mass somewhere between 150 and 265 times that of our Sun. Maybe more. It was born, astronomers believe, with as much as 320 solar masses. In the roughly 1 million years since it formed, it has been losing mass so violently, shedding the equivalent of entire solar systems' worth of material every year, that it has already burned through a significant fraction of what it started with. And it is still there, still burning, still holding together, in a universe where the physics explicitly says it shouldn't be able to. That contradiction doesn't get smaller the more you look at it. It gets bigger. To understand why R136a1 is so deeply wrong, you first need to understand the rule it violates. And to understand the rule, you need to understand what a star actually is. Because most people, when they think of a star, picture something permanent, something stable. The sun has been there every morning for every human life that has ever been lived. It will be there tomorrow. It radiates a steady, dependable warmth, and it has done so for 4.6 billion years without meaningfully changing. That stability is real. But it is also a kind of illusion. What looks like stability is actually a standoff. In 1926, the British astrophysicist Arthur Eddington worked out a mathematical boundary that describes this standoff with extraordinary precision. He called it, appropriately, the Eddington Limit. The idea is elegant and terrifying in equal measure. Gravity pulls inward, pulling all that mass toward the center, compressing it, heating it. Radiation pushes outward, the raw energy generated by nuclear fusion deep in the core, pushing up through the layers of gas, exerting pressure on everything above it. For most stars, including our Sun, gravity wins, not completely. Not by crushing the star into a point, but it wins enough. The star contracts, heats up, fuses hydrogen, generates radiation, and settles into an equilibrium. A long, stable, quiet equilibrium that can last billions of years. But add too much mass, and something changes. The more mass you pack into a star, the hotter and more luminous it becomes. Not gradually. The relationship is steep. Double the mass, and you more than double the luminosity. Triple the mass, and the luminosity increases far faster than that. At around 150 solar masses, the outward pressure of light, pure light, pouring up from the core, becomes so intense that it starts to exceed the inward pull of gravity. The star begins to blow itself apart, which means, by physics, nothing above roughly 150 solar masses should be able to hold together long enough to be observed. R136a1 weighs between 150 and 265 solar masses. It is not subtle about this. It does not hover just at the line. It is so far past the theoretical limit that the astronomers who first measured it spent months checking their instruments before they published. They reanalyzed the spectroscopic data. They ran the models again. They asked colleagues at other institutions to look at the same numbers independently. They checked again, and again, and again. The number did not change. Here is what you are looking at, if you could look at it directly, which you cannot. Not with your eyes, not safely, not from any distance we can currently reach. R136a1 is classified as a Wolf-Rayet star, a designation reserved for the most extreme objects in the stellar zoo. Stars so hot, so massive, so luminous that their outer layers are not held in place by the star's gravity at all. They are being continuously stripped away, blasted outward by the pressure of the star's own radiation. Its surface temperature sits at around 53,000 Kelvin. The surface of our Sun is roughly 5,800 Kelvin. R136a1 runs 9 times hotter. At that temperature, the star does not glow with visible light the way our Sun does. It radiates predominantly in X-rays and extreme ultraviolet, wavelengths that human eyes cannot detect, wavelengths so energetic they would pass through most materials without slowing. You could not stand near this star and see it, not because it is dark, because the light it emits would simply not register on the machinery of your eyes. It would pass straight through the fluid in your retinas without triggering a single photoreceptor. And then it would kill you. But that is a different problem. Its luminosity, the total energy it pours into the universe every second, is somewhere between 6 and 9 million times that of our Sun. Pause on that number. 6 to 9 million suns, packed into a single object. The Tarantula Nebula, that faint smear of light visible from the southern hemisphere, the one ancient sailors navigated by, glows the way it does largely because of this one star. The radiation from R136a1 alone ionizes the gas across dozens of light years in every direction, lighting up the nebula like a lamp inside a lantern. One object, lighting an entire nebula. In a galaxy that is not even our own. The problem with R136a1 isn't just that it exists. It's that physics cannot fully explain how it came to be this way. The standard model of star formation, the one that underlies virtually everything we teach in introductory astronomy, does not produce stars above about 150 solar masses from a single collapsing cloud of gas. Here is why. As a star forms, it generates radiation. The more mass it accumulates, the more radiation it produces. And at a certain point, the radiation it's generating becomes strong enough to halt the infall of additional material. Incoming gas gets blown back outward before it can fall in and add to the mass. The star regulates itself. It applies its own brakes. So where does a 265 solar mass object come from? The leading answer is uncomfortable. R136a1, a majority of astronomers now believe, did not form as a single star. It formed as 2, or possibly more, already massive stars in a very close binary orbit. stars so close that their gravitational interaction became unstable. They spiraled inward, closer and closer, until the gap between them closed entirely. They merged. Two already enormous objects, each carrying the mass of dozens of suns, colliding and fusing into a single body. The result was something larger than either could have been alone. A star born from a catastrophic collision of other stars. A star that exists only because something terrible happened first. And here is what makes that answer strange. It means that when you look at R136a1, you are not looking at a single object with a single history. You are looking at the surviving remnant of a disaster. A merger that should have destroyed what it created. An accident that accidentally produced the most massive star we have ever found. Here is the part that most coverage leaves out. R136a1 is not just massive. It is currently operating at roughly 80% of its own Eddington limit. Read that again. The Eddington limit is the point at which radiation pressure exceeds gravitational pull and the star blows itself apart. R136a1 is running at 80% of that threshold. Right now, at this moment, our Sun runs at a fraction of a percent of its own Eddington limit. It has enormous headroom, a vast, comfortable safety margin built into its existence. R136a1 has almost none. It is in a continuous state of barely controlled destruction. The outer layers are not held in place. They are peeling away constantly, blasted outward by the star's own radiation in what astronomers call a stellar wind. But the word wind does not do it justice. These are streams of superheated plasma accelerating outward at speeds of thousands of kilometers per second. The material being lost is not trivial. This star is shedding the equivalent of entire Earth masses worth of material every few hours. Not every year, every few hours. The star is dissolving itself in real time. At the rate it is currently losing mass, R136a1 will exhaust its hydrogen fuel in approximately 3 to 4 million years. For comparison, our Sun has been burning hydrogen for 4.6 billion years and has roughly 5 billion remaining. Its entire lifespan will be something like 10 billion years. R136a1's total lifespan from birth to death is roughly 3 to 4 million years. That is not 10 billion. That is not even 1 billion. 3 to 4 million years is shorter than the time that has passed since our earliest hominin ancestors stood upright on the African savanna. The most massive star we have ever found will live for less time than it took our genus to emerge. It is not a long-lived monster. It is a brief, catastrophic one. And the death it is heading toward will not be quiet. A star this massive does not die the way ordinary stars die. Our Sun, in 5 billion years, will swell into a red giant, swallowing the inner planets, then slowly shed its outer layers into a cloud of expanding gas. What remains, the core, will cool over billions of years into a small, dense white dwarf about the size of Earth. It will be faint. It will be cold. It will be old. But it will still exist. R136a1 will not leave a white dwarf. When a star above roughly 20 solar masses exhausts its fuel, the core does not slowly collapse. It falls in milliseconds. A core the size of a planet compresses to a sphere roughly 20 kilometers across, the density of an atomic nucleus, stretched across an object the size of a city. The energy released in that collapse, in those milliseconds, exceeds the total energy our Sun will emit across its entire 10 billion year lifespan. This is a core collapse supernova. The outer layers of the star are blasted outward at a significant fraction of the speed of light. The explosion briefly outshines entire galaxies. The remnant, a neutron star, is left spinning in the wreckage. For a star as massive as R136a1, it does not stop there. Above approximately 40 to 50 solar masses, the collapse can be so extreme that the neutron star itself is unstable. The remnant collapses further. Nothing remains. Not a pulsar, not a magnetar, not any object you can point a telescope at and measure. Just a black hole. The entire mass of hundreds of suns, compressed to a singularity. What R136a1 leaves behind, in 3 to 4 million years, will be a black hole. Not a stellar corpse, not a fading remnant. A hole in space-time where one of the most extreme objects in the known universe used to be. The physics that could not fully explain how it was born will have the same trouble explaining what it becomes. Here is what R136a1 quietly tells us about everything we thought we knew. We built our models of stellar evolution on what we could see and measure. We derived the mass limit from theory and confirmed it observationally, again and again, across thousands of stars. The upper limit was around 150 solar masses. It was consistent. It was solid. And then we found this. Not at the edge of the observable universe, somewhere too far away to study properly. 165,000 light-years away, close enough to observe in detail, close enough to take spectra, measure temperatures, model the wind, something that should not exist, sitting close enough for us to study it. The response from astrophysics was not to abandon the models. It was quieter than that. The textbooks added an asterisk. Binary mergers under specific conditions might allow for stars exceeding the standard limit. The boundary was revised upward, slightly. But the deeper question didn't go away. R136a1 is 1 million years old. In cosmic time, that is nothing. Our Sun is 4,600 times older. The Milky Way is 13,000 times older. R136a1 formed, in cosmic terms, yesterday, which raises a question that nobody has a complete answer to. How many objects like this have already lived and died in the history of the universe? How many stars between 200 and 400 solar masses formed in the first billion years after the Big Bang, when conditions were different, when the early universe was denser and hotter and more chaotic, burned for 3 million years, and collapsed into black holes before our solar system existed? We have no way of counting them. The black holes they left behind do not announce themselves. They do not emit light. They do not pulse like pulsars or flare like magnetars. They simply persist, warping space-time around them, accumulating mass from anything that wanders too close. And every time we detect a gravitational wave, every time two massive black holes merge somewhere in the distant universe and send ripples through space-time that our detectors can barely register, we are hearing the final echo of something like R136a1. Something that lived briefly, burned impossibly bright, collapsed into darkness, over and over across the history of the universe, before the Earth existed, before the Sun existed, before the first complex molecules assembled themselves into something that would eventually become us. We found one, still alive, close enough to study, right now. That is not guaranteed to happen again. There is something that has stayed with me since I first read about this star. Not the mass, not the luminosity numbers, not even the death that is already in motion. This, the light you would see if you could stand safely at the edge of the Tarantula Nebula and look at the star with your own eyes, left R136a1 165,000 years ago. 165,000 years ago, anatomically modern humans had barely left Africa. The oldest known cave paintings were still more than 100,000 years away. The entire recorded history of civilization, every empire, every library, every war, every discovery fits inside a small fraction of the time that light has been traveling toward us from this star. The star that produced that light has been burning the whole time. 1 million years of continuous, barely controlled destruction. 80% of the Eddington Limit every single day for 1 million years. And it has roughly 3 million more to go. We caught it at the earliest quarter of its life. When it finally dies, no human will see it happen in real time. 165,000 years is too far. By the time the light from the supernova reaches us, whatever we have become will look nothing like what we are now. But the explosion itself will be visible. When R136a1 collapses, when the core falls in milliseconds and the outer layers are blasted outward, the supernova will briefly outshine the entire Large Magellanic Cloud. From Earth, without any telescope, a new star will appear in the southern sky, brighter than anything near it, something that was not there before. It will fade over weeks, and then it will be gone. And where R136a1 was, there will be a black hole. And the physics will need another revision, because whatever this object is, however it formed, however it has managed to hold itself together for 1 million years in open defiance of the equations, it keeps pointing at the same conclusion. The universe does not ask permission. It does not wait for our models to catch up before doing things we said were impossible. It simply acts, and exists, and burns. And occasionally, if we point the right instrument at the right patch of sky, we get to watch.